Hello everyone, welcome back to my channel. In our today's video, we'll be continuing with the coordination compounds. And today we'll be learning about isomerism in coordination compound. And to be very specific, the structural isomerism. So, as we know what isomers are nothing but two or more compounds having the same chemical formula but different structural formula, or sometimes different spatial arrangement. They have different arrangement in space, but having the same composition or the similar chemical formula or the same chemical formula. That is what actually we call it as isomers. So whenever anyone say isomer are nothing but two or more compounds having the same chemical formula but different structural arrangement or arrangement in space. When they have different structural arrangement but have the same chemical formula, we call them structural isomerism. But the same, when they have the same chemical formula but different arrangement in space, that is what we call as stereoisomerism, or sometimes known as space isomerism. Okay, so in our today's video, we'll be trying to confine ourselves only in structural isomerism. We'll be not going into the other types of isomerism. So in our today's video, we'll be learning about structural isomerism in coordination compounds and try to understand that how many types of structural isomerism do exist in coordination compounds and what are they, and with various examples. So without any delay, let us start with first the definition of structural isomerism, okay, or isomer. So definition. Two or more substances, that's what I have told you, or molecule or compound having the same molecular formula. Okay, their molecular formula or composition, which we say, is exactly same. They have the same type of atom, same type of group, and same number of group or atoms, but different structural arrangement. Sometimes the bond may be different. Okay, sometimes the bonding between the metal and the ligand is different. Okay, sometimes the ions, the counter ions are different. But altogether, if you see, their composition will be exactly same. They will be having the same chemical formula, but different structural arrangements. Okay, that is why we call them structural isomers. Now, coming for the different types of structural isomerism. So remember that when we talk about types of structural isomerism, we are talking about coordination compounds. Okay, so different types of structural isomerism in coordination compound. So the first type of structural isomerism in coordination compound is ionization isomerism. Remember that whenever we say ionization isomerism, by the term itself, ionization. So whenever you will have a salt, okay, where you will have a complex ion, either cation or anion as complex ion, or so what happens is when they dissociate, okay, let's say two or different compounds, okay, you have two different compounds or three different compounds, okay, and then when you see their composition, when you see their molecular formula, they look exactly same, or their molecular formula is exactly same, okay, but when they dissociate in solution, they give you different types of ions. They don't give you the same ion. Such isomerism is known as ionization isomerism. So it is one of the structural isomerism. So the definition says that compounds which give you different ions in solution, although they have the same composition, are called ionization isomers. Okay, so what are ionization isomers? They have the same composition, no doubt, same molecular formula or same chemical formula. But when they ionize in solution, when they break into cation and anion, then the cation and anion is different. Now, to make it understandable for you, let me give you one example. These two examples are nothing but an example of ionization isomers. So you can see CONH35 Br. Okay, SO4 and CONH35 SO4Br. If you see both the compounds, they have one cobalt, 5 amine group, or you can say ammonia, one Br and one sulfate, SO4. But if you see, if I dissociate it, so let me take the first one and dissociate it. See, if I dissociate it, what I'll get? CONH35 Br SO4. If I dissociate into cation and anion in solution, what I'll get? CONH35 Br 2 plus. Why 2 plus? Obviously, the counter ion has a valency of 2 minus, sulfate, SO4, 2 minus. Same thing, if I dissociate the second one, CONH35, SO4, that is the ligand now. Okay, and plus, because the counter ion Br is Br minus. See the difference? Having the same composition, but different types of ions are produced in the solution. So when you have 2 coordination compound or 3 coordination compounds whose chemical formula is exactly same, you dissolve them in a particular solution, or when they are in solution, ionize to give you different ions. Then they are called ionization isomerism, by the name itself, ionization. Okay, so that is how we can understand the first type of structural isomerism. Let us try to go for the second type. Okay, in the second type of isomerism, which we call a solvate or hydrate. Solvate comes from solvent. Hydrate is basically water. Okay, so whenever your solvent is water, we call it hydrate isomerism. So what happens in this kind of isomerism is, again, obviously, if they are isomer, they will have the same composition, no doubt. But these two isomers, they differ in the number of solvent molecules. Remember that there are many solvent molecules which can act as a potential ligands. So if there is one such solvent which is present, or the solvent which you are taking as a medium may be a potential ligand, that solvent may act as a ligand also, but sometimes that solvent remain in the molecule as free solvent molecule in the crystal lattice of that particular compound. In simple words, we call them as water of crystallization also, if it is water. Okay, like when we write copper sulfate, we write CuSO4 5H2O. That 5H2O is existing as free solvent molecule in the crystal lattice of copper sulfate. So in the very similar way, obviously it is not always that it should be water. It can be any other solvent. But if it is water, then we call it hydrate isomer. If it is other than water, but obviously can act as a solvent, then we call it solvate isomers. Okay. For example, if we have this, see, you can see clearly in the first example, you have CrH2O6 Cl3. So your solvent in this case is water, H2O. And can you see in the first case that H2O is acting as a ligand, all the water molecule. In the second case, if you see CrH2O5Cl. So can you see there are 5 water molecules which are acting as ligand. But can you see the sixth one? Now it is actually attached to the molecule as free solvent molecule. Okay, or you can say water of crystallization. And if you see the third one, where there are 4 water molecules which are acting as a ligand, and the 2 other are acting as water of crystallization. So that's what. So if you have a difference, but if you see all together the composition of all these 3 molecules, they have 1 Cr, they have 6 water molecule, and they have 3 chloride group or Cl group. Okay, so altogether they have the same composition, but if you try to see the way they are different from one another is only because of the solvent molecule in one case is acting as ligand, in another case acting as the free solvent molecule in the crystal lattice. Or if it is water, we can call it water of crystallization. So whenever you see difference between one particular ionization or one particular coordination compound and the other coordination compound in this way, then we always call it the solvate or hydrate isomerism. Okay. Coming for the next, that is linkage isomerism. So what is linkage isomerism? By the name itself, link, bond. Okay, so remember that if anyone will ask you what is linkage isomerism, the first thing which should strike you is ambidentate ligand. Now, in our previous video, we have discussed what is ambidentate ligands. Ambidentate ligands are nothing but unidentate ligand which have more than one donating site. Okay, or there are more than one atom which can act as a donor. So this kind of linkage isomerism can occur in particular molecule, in those molecules where there will be ambidentate ligands. Okay, what will happen? In one molecule, it will donate from one particular site. In another molecule, it will donate from the another site. So the difference between the one isomer and the another isomer will be just on the basis of the donation of a particular donor group from the the ambidentate ligands. Okay, so for example, See this particular molecule, CHCONH35ONO. When we write ONO, we call it O-nitrito also. So basically what we are trying to show by writing in that way is the oxygen is responsible for donation of the electron pair to cobalt. But in the second case, you can see CrNH35NO2. When we say NO2, that means nitrogen is donating the electron pair to cobalt. So in one case, oxygen is donating, and in another case, nitrogen is donating. So see, it is the same ligand. Okay. In simple word, it is nitrite only, NO2 minus. But in one case, oxygen is donating. We call it O-nitrito. In another case, nitrogen is donating, N-nitrito. These are called ambidentate ligand. If I can show you one more example, like CrH2O5SCN. Okay. CrH2O5NCS. SCN. Sulfur is donating. NCS. Nitrogen is donating. So whenever we talk about this kind of difference between the two molecules, but having the same composition, if you can see, composition is exactly same. The only difference is in the link of the ambidentate ligand with the metal. That's why we call it linkage isomerism. Okay. Coming for the next and the final type of the structural isomerism, and which is nothing but the coordination isomerism by the name itself. The coordination over here stands for the coordinate covalent bond itself. Now, this kind of isomerism will take place only in those molecules. Remember that, only in those molecules which will have both the cations and anions as complex ions. Remember that usually we have coordination compounds where we have either the cation as the complex or the anion as the complex, and the other counter ion are usually the simple ions. But there are cases which I have shown you in the earlier videos also, that we may have both the cations and anions as complex ions. In such cases, what may happen is there may be actually, or they may differ in the distribution of the ligands. Okay, so there may be exchange of the ligands between the metal. Just to show you one example, CONH36, so cobalt is bonded with NH36, that is the cation part. CrCN6, that is the anion part. Chromium is attached with cyanide. Just see the another one, chromium is bonded with NH3 and cobalt is bonded with Cn. So whenever it happens that cobalt is, see, in the first case, cobalt is bonded with NH3, and the second case, cobalt is bonded with Cn. So they are exchanging. There is the distribution of the ligand in the cation and anion is varying. Okay, but overall composition 6NH3, 6NH3, 1 Cr, 1 Cr, 1 cobalt, 6 cyanide, 6 cyanide. Everything is same, but just they are differing in the distribution of the ligands in the cation and anion. The other things are same. So basically the difference is in the coordinate covalent bond. Cobalt is forming coordinate covalent bond with amine in the first case. In the second case, cobalt is forming coordinate covalent bond with cyanide. In the first case, chromium is forming coordinate covalent bond with cyanide. In the second case, chromium is forming coordinate covalent bond with NH3. So that is why we call it coordination isomerism. So it will occur only on those cases where we have both the cation and anion as complex ion. Otherwise, it will never occur. So this is how you have to remember. So whenever we say structural isomerism, there is a difference in the counter ion and the ligand. The counter ion also act as a potential ligand. So they can replace one another. Whenever we talk about solvate isomer, there is a difference in the ligand as water molecule, as ligand, okay, and as the water of crystallization or as free solvent molecule in the crystal lattice. When we talk about linkage isomerism, it's about ambidentate ligand. And whenever we talk about coordination isomerism, we are talking about those complexes where cation and anion both are complex. So there is a specific case where this isomerism occurs. So if you remember this specific case, we know what kind of isomerism this particular type of compounds will show. And that is how actually we can understand structural isomerism in a very easy and convenient way. So that is all about the structural isomerism in coordination complex. So thank you, everyone. Do subscribe for this channel for explanation on various topics in chemistry. Thank you.